Autonomous vehicles, or in SEA parlance, cars with L4 driving automation, meaning that humans are not in control of the vehicle, are not yet fully specified. There is no universal agreement on the type of sensors, the number of sensors, the placement of sensors, and the type and amount of processing. Furthermore, the hardware and software stacks for L4 trucks, L4 robotaxis, and L4 passenger cars will all be different. Trucks require longer range on the highway because of their higher mass. Robotaxis need to find ride-hailing passengers at long lateral distances. And passenger cars need to look beautiful, with no ugly sensors hanging off the car chassis. Safe and reliable. To look into the future of autonomous vehicles, we first need to look into the past. In the summer of 1996, little did I know that I was at the very beginning of an autonomous mobility revolution. For the 2007 DARPA Urban Challenge, the Velodyne HDL-64E LiDAR was mounted atop 5 of the 6 vehicles that finished. LiDAR provided reliable, high-resolution point clouds of the surrounding environment, which vastly simplified the problem of mapping and perception, such that the problem could be solved on a vehicle-mounted mobile computer, with only a few kilowatts of power draw, limited by the vehicle battery. No supercomputer or server room needed. In other words, LiDAR made it possible to solve the autonomous vehicle problem on a computer small enough to put into a car. Although LiDAR enabled autonomous driving in rural and urban environments, the first-place winner of the 2007 DARPA Urban Challenge had an average speed of only 14 miles per hour, in part limited by the short range of the LiDAR, approximately 50 meters at the time, and density of points, only 64 scan lines. Since 2007, LiDAR has improved slowly in range, approximately 150 meters, and density of points, approximately 128 scan lines. But it still does not meet the requirements for highway driving at high speeds, which requires denser sampling and longer range. The maximum range of LiDARs is unlikely to increase significantly since the transmit laser power is limited by eye safety concerns. Thankfully, other technologies have filled this gap. One such technology is the wide baseline stereo vision camera, which, like LiDAR, offers reliable depth measurements. LiDAR measures distance by directly measuring a physical quantity, the round-trip time of flight of a laser pulse from the vehicle to an object. The distance to the object is proportional to the time of flight, which is a direct measurement, unlike neural network approaches, which are indirect measurements that can only infer the desired quantity from 2D image data. Just like LiDAR, stereo vision directly measures a physical quantity, angles. The angle subtended between an object and 2 cameras with a known baseline distance directly yields the distance to the object, which is exactly the principle of triangulation. But unlike LiDAR, wide baseline stereo vision cameras offer longer range and denser sampling to capture any small object in the road, further improving reliability and safety, even in harsh weather, and fueling renewed interest in stereo vision cameras for autonomous vehicles. Another non-obvious benefit of long-range sensors that can see beyond 150 meters is the ability to push computations to the cloud. A car traveling at 67 miles per hour or 30 meters per second takes 5 seconds to traverse 150 meters. As a car plots optimal trajectories and detects objects in the road, for example, 5 seconds is enough time to double-check results from its onboard computer against more robust and comprehensive algorithms running on more powerful computers in the cloud, especially with the promise of 5G networks with 1 millisecond latencies. As networks become more reliable and sensors have longer ranges, expect this powerful combination of sensors and computers to further improve the safety of autonomous vehicles. As a side note, a single-channel scanning LiDAR would require 5 seconds to measure distances, the equivalent of a wide baseline stereo camera with 5 MP CMOS imagers, since the round-trip time of a laser pulse to an object at 150 meters is 1 microsecond. When repeated for 5 million points, it takes 5 seconds to scan the scene. With the scan time limited by a fundamental physical constant, that being the speed of light, this is a fundamental limitation of LiDAR. Therefore, an autonomous vehicle with a single-channel LiDAR would not be able to scan ahead fast enough to see, for example, a brick at 150 meters before hitting it. AV software and hardware today. Currently, 94% of the 35,000 fatal crashes on U.S. roads each year, or about 12 deaths per 100,000 people, are caused by human error. The Insurance Institute for Highway Safety reports that the current car fatality rate is 1.34 deaths per 100 million miles traveled. Some experts estimate that rate could decrease by a factor of 10 by removing accidents caused by drunk drivers and texters, another metric in favor of AVs. To see the road, autonomous cars rely on cameras, radar, and LiDAR, or laser radar. By bouncing a laser off an object and measuring the return time, LiDAR can judge distances and see in 360 degrees. If high-resolution sensing tools are the eyes of self-driving cars, their cognitive abilities come from intelligent algorithms and artificial intelligence that interpret this raw data against reference maps, says Shravan Puttagunta, former CEO of California-based Civil Maps. According to Puttagunta, the Civil Maps platform, like those of competitors Mobileye, Delphi, and Brightbox, gives an autonomous vehicle contextual awareness, not just a 2D navigational map. It uses artificial intelligence to process raw data coming from high-resolution laser imaging, so cars can localize precisely and make better tactical decisions, like what to do at a four-way stop or roundabout. Quote, "What we're working on is the problem of AVs having an abundance of caution," says Paul Newman, founder and chief technology officer at the Oxfordshire-based driverless vehicle software company Oxbotica. How is an AV going to be appropriately assertive at a rotary? Because the worst thing you can be is unknown, unsafe. There's all kinds of noise and religion about the right algorithm you should use, Newman adds. I think that's all for the birds. It's an architectural systems problem. Are self-driving vehicles the future of logistics? AV technology has advanced dramatically since Japan's Tsukuba Mechanical Engineering Laboratory launched the first semi-automated car in 1977. Commercial vehicles like forklifts and mining vehicles have been operating autonomously for decades, Newman says. Now, autonomous last-mile delivery vehicles are cropping up in cities such as Houston and Mountain View, California. Neuro's zero-emission refrigerated minicars are backed by brands such as Kroger, 7-Eleven, Domino's, Walmart, FedEx, and Chipotle. They operate on renewable energy from wind farms in Texas and carry as much as 500 pounds of groceries, according to a company spokesperson. These small-scale urban mobility vehicles could be integrated into broader supply chain networks in which electric autonomous fleets running nearly continuously could transport goods faster, more safely, and with less fuel. Quote, "The first use cases are going to be places where we can use the vehicle as many hours per day as possible because they're expensive," Chase says. So that means taxi-type services, delivery, or trucking. Aurora, which acquired Uber's self-driving division in 2020, is pilot testing its AV software with Werner Enterprise tractor-trailers on a 600-mile span of highway in Texas. FedEx and Uber Freight have run similar programs elsewhere. Scaled across long, monotonous stretches of highway, similar AV platoons could narrow a gap in the national shortage of qualified human drivers. Changing the roads of the future. It could be years or decades before self-driving cars become a mainstay of cities and highways, says David Zuby, Chief Research Officer at the Insurance Institute for Highway Safety. Ensuring safe coexistence with other vehicles is a key hurdle. Fully autonomous vehicles, at least for now, must share roads with cars operated by human drivers and those with conditional autonomy. Both present safety risks. The National Highway Safety Administration defines levels of driver assistance technology from 0 to 5. At level 0, the driver is fully responsible for the vehicle and must remain engaged and attentive at all times. At level 5, occupants act only as passengers and do not need to be engaged. Most private and commercial vehicles operate somewhere in the middle, level 1 to level 3. Inexpensive. Cars need to be mass-produced to the tune of 100 million cars a year. Even $1 of savings per car is significant when multiplied by the number of cars produced per year, which is why all the electronics and software needed to make cars autonomous must be inexpensive. This means that the software must run on commodity automotive SoCs. The number of sensors must be reduced to the bare minimum needed for safety. The sensor type will favor low-cost technology such as radar and cameras, and insofar as possible, computation will be pushed to the cloud. Sensors that do not provide independent measurements and have similar failure modes, that is, LiDAR versus cameras, will be filtered, and only one will prevail. Thank you for watching, and please hit the like button, subscribe to the channel, and enable post alerts to view more of our future videos. After saying that, keep watching our videos, and I'll speak with you in the next one.